So why don't I introduce you now at this point and then get going. Okay. So welcome everybody to what I believe is the last physics colloquium of the quarter. And it's my great personal pleasure to welcome Vicky Kaspi from McGill University. Vicky was actually an undergraduate, I think, at McGill, and then moved to Princeton, and then to MIT, where she was on the faculty before moving back to McGill, where she's is obviously professor and has had various roles there, including director of the McGill Institute for Space Research, and has been a dean there, and is also a program director for a large part of the Canadian CFAR program, and that's what things you can tell us about. Vicky's research, major research interest has involved neutron stars. In particular, as a graduate student, she worked with Joe Taylor and Dick Manchester and Andrew Lyne and others, and developing the increasingly precise business of pulsar timing, which has been such a boon for testing general relativity, as we heard from Maureen McLaughlin a few weeks ago. She more recently, she's been interested in understanding a major astronomical puzzle, which is the nature of fast radio bursts. And in doing this, she has used very, very productively a telescope, which is going to tell us about, a Canadian telescope called CHIME, which was originally designed and is still and is obviously used for doing cosmology, but the same telescope can also do double duty in studying pulsars. And the topic of today's lecture, which is going to be fast radio bursts, a cosmological conundrum, and why I left the galaxy. And before I let Vicky go, I would like to say that amongst her many honors and awards has been one that just came overnight, which is she shares the Shaw Prize with Vicky, with Krista Kuviliotu, excuse me, and that's a great excitement, and it's for her work on magnetars, which is, as you will hear shortly, I don't want to steal her punchlines, but you will hear shortly, is a large part of the story that is emerging of fast radio bursts. So allow me to congratulate you, Vicky, on this award, and also say how much I'm looking forward to hearing your current views on fast radio bursts, a cosmological conundrum, or why I left the galaxy.
Okay, well, thank you very much, Roger. It's a real honor to be giving this talk, and it's thus far not totally computable honor to have won the Shaw Prize back to back with you. That just doesn't quite, I can't wrap my brain around that. But in any case, thank you for that very generous introduction. I'm going to go ahead and share my screen. I hope you can all see my slides. So yeah, so I'm going to be talking to you about fast radio bursts, and I must remember to bring up the chat because I do hope you will all, here it is, that you will feel free to ask me questions throughout the talk. I'm very happy. You know, with Zoom, it's so hard to know that you're all there even, and that you can hear me and I can't see your faces. So please don't hesitate to ask questions. So, you know, when people ask me, what am I working on these days? I sometimes say, I don't know, because I don't really know what fast radio bursts is. And I hope by the end of the talk, you'll understand what I mean by that. It's the new astrophysical puzzle, relatively new, and has had a lot of twists and turns as we try and figure this thing out. But before I tell you about fast radio bursts, I want to tell you about the time when I lived in the galaxy. And, you know, I'm not going to I'm going to tell you now about radio pulsars and magnetars, what I've worked on for the past, for 20 odd years. And not just to give you a personal history, for a good reason, because there's a lot of what we know about radio pulsars and magnetars will end up being really relevant to fast radio bursts. So what are radio pulsars? My pulsar isn't rotating there. So I think you probably all know that radio pulsars are rapidly rotating, highly magnetized neutron stars, and celebrated with Nobel Prizes for tests of relativistic gravity. They emit across the electromagnetic spectrum, although they're most commonly observed at radio wavelengths. I guess at Stanford, you know all about gamma rays from millisecond pulsars in particular, because of Fermi. But in any case, the vast majority, some over nearly 3,000 now, are known, observed in radio waves, and their emission is all powered by their rotation, or more specifically by the rotational kinetic energy loss due to magnetic braking. And that's ubiquitously studied, and certainly Roger's very interested in that topic and made a lot of contributions. You can see some actual radio pulsar data, where you can see some individual pulses. This is actually data that I took at the Green Bank telescope. Here's the Green Bank radio telescope in West Virginia. You can see, and I'm pointing this out for very good reason, this is a super honking bright radio pulsar where you could see every single radio pulse. That's not often true. You can see some pulses are weaker than others. And there's pulsars where one pulse hugely dominant, is incredibly bright, and then the others you can't even see unless you did like some nice Fourier transform or something. You see huge modulation. Sometimes some pulsars have giant individual pulses. But one important property of radio pulsars, super relevant to FRBs, is that the pulses arrive at Earth dispersed by interstellar plasma. And so what I mean by that is that if you look at some radio observations, so some bandwidth here between about 400, 460 megahertz, and you look at when the radio waves, when the radio burst from the pulsars arrives as a function of radio frequency, what happens is that at lower radio frequencies, the burst arrives later. And in this case, in this plot, what you can see is that it wraps around. So the delay across this band due to this dispersive effect is actually many pulse periods in this case. So you can see the pulsar signal wrapping around. And the degree of this dispersion, the slope here, we call basically the dispersion measure, this DM, which is proportional to the integrated electron density along the line of sight to the source. So that's NEDL. Typically, we measure it in parsecs per cubic centimeter because of that integral there. And what you can see is that the time delay between any two radio frequencies is proportional to TM and to 1 over that frequency squared. So this delay here is actually parabolic. It might not be obvious in the plots, but it is. Now, this dispersive effect absolutely must be corrected when observing radio pulsars. Otherwise, in this case, you see, if you just summed up the band, the whole pulse would be washed out. So we introduced delays in the signal as a function of frequency to correct, to de-disperse the radio pulses. That's how we study them. And so for each pulsar, we measure a dispersion measure. And so for the 3,000 odd radio pulsars we know of in the galaxy, we actually know their distribution in the galaxy. And many of these pulsars have independent distance estimates. And so by using the dispersion measures and independent distance estimates, we can make a model for the dispersive material, which is, we believe, is free electrons. It's basically free electrons is cold plasma dispersion. So the free electron density is known everywhere in the galaxy from radio pulsars. So we developed these models. This is one by Cortez and Lazio. If you were looking down on the Milky Way, here's the center of the Milky Way, and this Pac-Man kind of figure here, that's where the solar system is. You can see the spiral structure. And these are contours of constant dispersion measure in units of parsecs per centimeter cubed. And so, and this is, the model, by the way, is a three-dimensional model of the galaxy. And this is just a slice through galactic latitude 0. And so what you can see is that if you measure a dispersion measure toward a pulsar in the galaxy and you know which direction you're looking, you know roughly the distance. So it's calibrated using pulsars with known distance estimates, but then you can use it to then infer distances for other radio pulsars. And in particular, the model has a maximum. So the free electron distribution in the galaxy eventually runs out as you move further and further away from the galactic center. And for any direction in the galaxy, there is a maximum value of the dispersion measure. Now, of course, knowing what that maximum is depends on how your pulsars are distributed in the galaxy, but these models, in any case, have a maximum. And one other property of pulsars I want to mention is that they rotate, as I mentioned, with some spin period p, and that spin period is increasing with time because they're losing rotational kinetic energy. And that p and that p dot, the time derivative of the pulse period, are really valuable and very easy to measure. These are measured for all radio pulsars. And once you know them, you can infer a whole bunch of interesting pulsar properties. One is the spin down luminosity, the rate of loss of rotational kinetic energy, the time derivative of your rotational kinetic energy, where I is the moment of inertia, omega is the angular velocity. And that's the energy source for all of the radiation that we detect from pulsars. And the maximum known, by the way, for this is from the Crab pulsar. Oh, there's the Crab. Just to remind everybody, it's about somewhere between about 4.5 times 10 to the 38 ergs per second. That's the maximum spin down luminosity that we know for a radio pulsar in our galaxy. You can also infer a rough age for the pulsar. P over 2 p dot is a characteristic age. Those range from 1,000 years to a billion years in some cases. And you can also infer, assuming magnetic dipole breaking in a vacuum, magnetic field for a radio pulsar goes as the square root of p times p dot. And the maximum there is known, for radio pulsars, it's around 10 to the 13 Gauss. Although I put a little asterisk here, I put asterisk to remind myself to say for the Crab pulsar, the spin down luminosities, that is a maximum for the luminosity of any of the rotational, of any of the electromagnetic radiation we'll see from that. And when you see giant pulses, for example, from the Crab, they still don't go above that rotational, that spin down luminosity. And for the magnetic field, I say the maximum known is a few times 10 to the 13 Gauss for radio pulsars, but there's another class of young neutron stars, which we refer to as magnetars, that have magnetic fields inferred in the same way from the spin down rate to be greater than 10 to the 14 Gauss, in some cases 10 to the 15 Gauss, where that's a magnetic field on the surface near the equator. And these are also quite young. Typical ages are less than 10,000 years. And, with these strong magnetic fields on the surface, which are almost certainly much stronger in the interior of the neutron star, the total magnetic energy reservoir is enormous, 10 to the 47 to 10 to the 49 ergs. And with so much magnetic energy and such strong magnetic fields, you have instabilities in the fields. The fields tend to decay, which tend to stress the crust, which tend to twist field lines. And you see these massive explosions of X-rays and gamma rays. These are observed ubiquitously from the roughly 24 magnetars we know of in our Milky Way galaxy, which are about, by the way, we catalog them, the McGill magnetar catalog. You can have a look there. So these are really bright in X-rays and gamma rays, and a small handful have shown radio emission as well. But their radio emission has not, over the years we've studied, it hasn't been particularly bright. I meant to mention that, the spin down luminosity, when you go back a slide here, note that it goes like P dot over P cubed. So if you have a long period, and magnetars tend to be long period pulsars because their magnetic fields are so strong, they've slowed down a lot. They don't have much spin down luminosity. We think the X-rays and gamma rays are not coming from that, but the radio emission probably is, and it's very low luminosity. Magnetars can have giant flares, which are the most intense cosmic transients ever observed in terms of flux at the Earth. They saturate satellites. You can see here this giant flare in 2004 from the soft gamma from the magnetar 1806-20, also known as soft gamma repeater. The luminosity is 10 to the 47 ergs per second. You see saturated detectors here, and I just want to note this is a work by Kevin Hurley, published in Nature. Kevin is a pioneer in magnetar physics, has done tremendous work in this area. But curiously, the radio wave, the giant flare didn't show any radio waves. So it so happened Parkes was observing at the Parkes radio telescope in Australia, was observing the sky when this thing went off, and we did not detect any, just by luck, we did not, it was observing, and we did not detect any radio waves. Now, this is probably a good time to start because I'm about to leave the galaxy. So let me first verify that everybody's still online. Are you all still there?
We're here.
Oh, good. Yay.
We're here.
Okay.
Sure.
That's nice to know. So just tell me, are there any questions? Not so far.
Well, I have a completely dumb question. Is it a coincidence that the Crab pulsar, which is famous for a number of things, is also has the highest luminosity? Is that because of some obvious fact of its life? It's young. It's I don't know what.
It's not a coincidence. It's that it has both a large spin down rate and a very short period. So pulsars are born spinning fast, and it hasn't had time to slow down. And so the spin down luminosity goes as P dot over P cubed. So if you have a small period, then the spin down luminosity is really high.
Sure. So is it the youngest pulsar also?
Yeah. Yeah, it's also the young. There might be one that's borderline young, and we know the Crab, of course, is dated to 1054 AD. So there's some that are kind of comparably young, but we don't know their actual birthdays. But it's probably the youngest in the galaxy. Yeah. Okay. Thanks for that question. So after 20 years of studying radio pulsars and magnetars, I decided to leave the galaxy. What made me leave? The Lorimer burst. So the Lorimer burst was an event that was found, it says 2017. No, that's wrong. It's a typo on my part, 2007 paper. It was found in a pulsar survey, and actually is a survey for single pulses. And what you see here is, a dispersed single radio pulse, where in this case, this is now the dedispersed, the inset is the dedispersed pulse. You see there's a huge pulse that lasts just a few milliseconds, and then nothing. And nothing comes back. So this thing doesn't return. You don't see it again. The horizontal line here, by the way, is some TV station. It's some fixed radio frequency. Not interesting, terrestrial interference. This was detected at the Parkes Observatory, and it immediately had people quite excited. And that's because for the Lorimer burst, in the direction the Lorimer burst was coming from, which is well out of the galactic plane, and in fact, toward the direction of the Magellanic Clouds, The maximum DM from our galaxy from models of the distribution of free electron density is about 25 parsecs per centimeter cubed. But the Lorimer burst had a dispersion measure of 375 in those units. And, you know, that was shocking. We had never seen this before. We'd never seen a DM higher than on the models. And you might say, well, what if there's some H2 region or some ionized material between us and the object within the galaxy, but people searched for it. If you have enough, that's a lot of dispersion measure, not a lot of free electrons you'd need. It should be bright and in thermal Bremsstrahlung or in recombination emission. Nothing else was seen there. And so this naively implies a cosmological distance and, of course, a tremendous luminosity, if so. Now, cosmological distance, well, at the time, the best models for the intergalactic medium's free electron density, and I will return to this point later, but we're roughly speaking, the DM in the IGM would be about 1,200 times the redshift, which would imply naively a redshift of 0.3 for the Lorimer burst. So that's about a gigaparsec, which is, you know, pretty far. But we also know that's likely to be an upper limit because some DM must be in whatever host galaxy this thing is coming from. So the total DM that we measure, you know, it's just the integral. So it's just the sum of all the different contributions to the DM. So there's a contribution to the ISM, the interstellar medium of the Milky Way, and also the Milky Way probably, you know, we think has some halo of free electrons. There's, of course, the intergalactic medium, which could consist of multiple other halos of any galaxies along the line of sight. And then there's, of course, the unknown host contribution to the DM, which would probably have some its own halo contribution as well. And so, you know, these you can sort of estimate, the Milky Way values you can kind of estimate. So let's say you subtract off the model and some estimate for the halo and then divide it equally between the IGM and the host. Let's say you take, you know, half, 500 megaparsecs. That's still quite a high luminosity, 10 to the 40, 10 to the 43 ergs per second. Now you might say, well, why don't you just look and see how far this thing is away? But you could determine the redshift, you could set the energy scale, and you could also know what kind of galaxy this came from. The problem is that the beam size of the 64-meter Park dish includes hundreds of galaxies. So there's, you know, it's something like a 13 arc-minute beam. You could try going to a larger telescope like Arecibo, as we might have in the past. Wonderful telescope. No longer with us. But even with Arecibo at these radio frequencies, L-band 1.4 gigahertz, the beam size is still much too large. Yeah, so there's many galaxies. What you really need is an interferometer, like the Very Large Array. The problem is with the interferometer, it's hard to detect these things. It has a tiny field of view. So the Lorimer burst is you know, was the first of many to be found, and they're all over the sky, but you can't predict when or where they're going to come. So the key properties of fast radio bursts, at least as of 2017, we know they were few millisecond bursts of radio waves. There had been about 24 detected as of 2017, but given the tiny fields of view of the Parkes telescope, where the bulk of them had been detected as of that date, you could infer an all-sky rate of something like 1,000 per day. So it was clear these are ubiquitous on the sky, coming from all directions. Most of them are singly peaked. Some of them are scatter broadened, like in this example here, where you can see the dispersive sweep of the single radio pulse. And these are now breaking up the radio band into 3 parts. If you look at near the top of the radio band, you see a narrower pulse, and you see this exponential scattering tail at lower radio frequencies, and that's due to multipath scattering, a phenomenon that we observe all the time in our galaxy for radio pulsars. Basically, its inhomogeneities in the electron density distribution cause delays that for radio waves would have gone in different directions, get sent back to the telescope direction, and that causes a one-sided time delay, which is pretty interesting. It's telling you something about the distribution of electrons along the line of sight. But some are multi-peaked. I'll show you examples of those later. Some have complex morphologies and some repeat. Of the Lorimer burst never repeated, but I'll talk more about repetition shortly. And the inferred luminosities, given the dispersion measures that we see and estimates of the distances, were in the range of 10 to the 35 to 10 to the 43 ergs, which is much, much higher than the sorts of individual pulse energies that I talked about for radio pulsars. You could see some recent reviews at those papers. Now, different models, for a while there were more models than there were events observed. That's no longer true, as you'll see. We know it has to be some sort of compact object just from the source size being, a few milliseconds long in terms of light travel time. The energies are not that constraining. Gamma ray bursts have isotropic energies that are, orders of magnitude larger. And you might wonder, are there GRB, FRB coincidences? And no, so far none. But we know, given the compact size and the luminosities, the brightness temperatures, is, if you assume a thermal model, which can't, just can't be right, you get absurd temperatures, which is the same as you see in radio pulsars, or at least the same phenomenon. Something non-thermal has to be present, which suggests a strong magnetic field, but we'll come back to that. And you might say, well, what about some sort of cataclysmic event like a supernova? Supernova, you can calculate the sorts of free opacities you expect. It's hard to get the radio waves out from supernovae. You might wonder about compact object mergers, but remember, we're detecting 1,000 per sky per day. That's a really high rate compared to what is known for neutron star neutron. Now, for these kind of mergers. And moreover, some of them repeat. So it's sort of hard to understand in terms of cataclysmic events when we know that they repeat. And there's actually a sort of living FRB theory guide at this website. You can go and see all the different theories as they get published. Now, the first repeater that we detected was found using Arecibo. We were very excited because this was the first non-Parkes event. And for some time, we were worried that maybe this was some sort of interference, that the whole FRB phenomenon was just terrestrial. But we found one. It was very exciting. You could see the dispersive sweep here. It had kind of a strange spectrum. We noticed that right away. It sort of is much brighter at the higher frequencies. That's really unusual for a radio source, for any astrophysical radio source. We assumed at the time it was just offset in the beam. There's phase space in the radio beam of the radio telescope for a flat spectrum source, or even in a normally inverted spectrum source to look like this. But then after we kept observing it on the sky, we discovered that, and this is actually my graduate student, Paul Schultz, who made this discovery, it repeats. And these were 10 repetitions that we saw in the space of an hour observation. This was after months of looking at it and seeing nothing. Here you can see them all. They're now de-dispersed and all to the same dispersion measure as the original Arecibo burst that we detected. And in this montage here of the different bursts, you just automatically see some phenomenology, right there in front of you. Some bursts from the source are really bright, and some bursts are really faint. And these two bursts are really just less than 10 seconds apart, and you see radically different spectra. Some spectra are totally band limited, it just peters out in the middle of the band. And they change rapidly. So that is phenomenology we had never seen in any radio pulsar or anything like that. We now know that the bursts from this source cluster in time, so it's not a huge surprise that we were watching and didn't see anything and then suddenly saw 10 bursts. It's non-Poissonian for this source. In fact, as I'll talk about, this source seems to be possibly periodic on a 150-day timescale. So that was, right away when we found that, it eliminated all the cataclysmic models. I think, you can't have neutron stars merging 10 times in an hour. So that was pretty exciting. But the other thing it enabled was localization. And oh yes, before localization, I just want to say here are some other examples of this FRB's bursts, and you just see all sorts of interesting structure. And this is downward drifts in frequency and interesting multi-component bursts. I'll come back a little bit later to that. Yeah, and so FRB repetition right away, some seem to repeat and some didn't. Why did this one repeat? Could there be different classes of FRBs? Are some cataclysmic and some not? At the time, it seemed though a possible coincidence of the few dozen FRBs that were known. The only repeater was also the only Arecibo FRB, where Arecibo's the most sensitive telescope. It could be that other telescopes like Parkes just couldn't detect repeat bursts without waiting a very long time because they're too faint. Now, when you find a repeater, then suddenly everybody starts talking about radio pulsars and magnetars again, which is why it was important to introduce them, so that I could explain why at least rotation-powered pulsar giant pulses like we see from the crab are really unlikely. We've now seen thousands of bursts from 121102, and as I'm going to explain, it's been localized to a gigaparsec, and the luminosities are just too high. You need spin down luminosities where you have the period really like less than a millisecond at birth, but lasting for many years, because we've now been observing 121102 for some time. And moreover, the efficiency for conversion of, I should have said this before, but in radio pulsars, the efficiency for conversion of the spin down luminosity into radio waves is really not high. So you need spin down luminosities much higher than the crab in order to explain the burst of 121102. And it really pushes the envelope for that source. And as you're going to see, we've had much more distant sources now. It's really hard to make it a rotation powered pulsar with giant pulses, at least in that case. But of course, you come back to giant flares from magnetars, and it could be, and let me come back to that. But as I said, one thing the repetition enabled, or maybe I should stop for a minute. Any questions? Are you all there? Hope you're all there.
We're still here.
Yay, okay. Anything, it's all clear?
I have one question.
Oh, yay.
Can Hera detect this?
Oh, at really low radio frequency?
Yeah.
There's a paper appeared on the archive just a few weeks ago, actually by lead author, my graduate student, Ziggy Polinis, who will figure in the talk later, that where LOFAR detected it at, I think the lowest frequency is 130 megahertz. So Hera is lower than that, I believe. And so the answer is we don't know. The scattering is potentially a big problem. I mentioned the scattering. The burst gets, elongated at lower radio frequencies. So you need one that's not very scattered. So we have one that LOFAR detected. That one maybe is detectable at Hera frequencies. Now, I don't know if Hera, though, has the, software and electronics that you need in order to do fast sampling like this. I mean, they have no need for fast sampling as far as I know.
I have a question. Now that Arecibo is not around anymore, has FAST taken its place and has done many observations?
Yeah, FAST is doing a fantastic job. FAST is first of all finding lots of radio pulsars, but also doing wonderful work on fast radio bursts. FAST can clean up on repeaters, for example. So as I'm about to tell you, we now have many repeaters from CHIME, and FAST can really study them, go really deep into the luminosity function, and also can search for repetition, can identify repeaters. They don't have a huge field of view, so FAST is going to be really useful for targeting sources discovered with large field of view telescopes like CHIME.
But perhaps just clarify for the audience that FAST is a big new radio telescope in China.
Yes. So sorry, I should have said that. It's 500-meter aperture, single dish radio telescope in China. So it's bigger than Arecibo was 300 meters. So very, very sensitive. Okay. Yes. Oops. So once we had the repeater, we could go to the very large array, Jansky very large array, which it's actually very computationally intensive to find pulsars with an interferometer, find short bursts with an interferometer, particularly dispersed bursts. And this is a project that was worked on by many people at the VLA, including led by Casey Law and other people, Sarah Burke-Spuller and others. And with as part of their work, which they were trying to do commensal searches for FRBs using the VLA, then we had something to point at. But it took a long time. We looked for many hours without detecting anything. And then finally, and we kept asking for time, and then I'm very grateful to the VLA people, they let us keep observing. Eventually, in the fall of 2016, in just the very first hour of test observation, we got a burst at the right, from the right position. Here's the Arecibo uncertainty regions are the black circles, and here that's the position in the end of the FRB, now known to an arcsecond, and subsequent, and you can see the dispersive sweep is exactly as you predict. And then subsequent VLBA, very long baseline array observations, and using the European very long baseline network, EVN, they also observed the source, and you could then localize it. So this was the first localization to a galaxy, and it was amazing because it was a dwarf galaxy. And so, we'd all been picturing in our minds big spiral galaxy or something, because we were thinking it could be a young source like a magnetar or spiral. It should be where the star formation going on. And instead it's in this little puny dwarf galaxy, but it was at redshift 0.2. So it confirmed the cosmological distance as inferred from the dispersion measure, which was a really nice thing. It's also coincident, by the way, with a continuum radio source that's highly variable. And subsequently, with the EVN and VLBA milliarc-second localization, we could confirm that it's in a knot of star formation within this dwarf galaxy, which did, in fact, suggest youth. So when you find it in a knot of star formation, that suggests that the source is quite young, which would be consistent with a magnetar kind of interpretation. So that was very exciting. And I'll just stop and say that the New York Times covered that localization and said fast radio bursts are traced to a faraway galaxy, but the caller is probably ordinary physics, which I found a little offensive. I mean, I wanted to just go to Dennis Overby and explode one in the middle of the night around his house and see how ordinary he found that. But meanwhile, at the New York Post, we never said they're aliens. But anyway. Since that time, there's been lots more host galaxies identified. I think today, all in all, there's 14 localized. And here's a montage of 6 more host galaxy of FRBs from the ASCAP collaboration. So the Australian Telescope SKA Pathfinder, the Square Kilometer Array Pathfinder telescope. This is an array, 36 dishes, each with a phased array feed. They can both detect FRBs. Now they don't have, they can detect, I don't know, something like maybe half a dozen per year. So they don't have tremendous sensitivity, but when they detect them, they have an arcsecond localization, even better sometimes. And so in the cases of these ASCAP FRBs, whose positions are indicated with white circles, and on top of these optical images of the field, they are all located near galaxies. And here's a beautiful one where it's right in the spiral arm of a massive galaxy. And all of these are fairly massive galaxies. And in fact, of the 14 that have been localized today, all but that in its first repeater, they're all pretty much in massive galaxies. And in fact, the majority of them are in spiral arms of galaxies, which says, so maybe they are young after all. Now, I should also mention that when you have localizations and you can then, first of all, you're interested in the type of galaxy and where it is in the galaxy, but you also have redshifts, then you have distances to all these galaxies. And so here's a beautiful paper in Nature by Macquart et al. 2020, where they took 5 what they called gold-plated localizations. They couldn't take all the localizations that are there, and they have some complicated selection criteria for which they choose. But in any case, if they subtract off the contribution from the dispersion measure due to the Milky Way galaxy, and they take some estimate for what the host galaxy dispersion measure contribution should be and for what the galaxy halo should be. And of course, those are not really well determined, but they take fiducial numbers that are reasonably well justified. And they plot the remaining intergalactic, which they call cosmic DM, versus redshift. You see something interesting. So the dots are the different fast radio bursts. And the line is not a fit. The line is the prediction for the given Planck cosmology for the baryons in the intergalactic medium. So there's been a long prediction that the intergalactic medium should be filled with baryons, which should be ionized. And this has been called the missing baryon problem. It's just hard to observe all of this material in the intergalactic medium when it's ionized. But of course, fast radio bursts, because of this cold plasma dispersion of radio waves, you can measure, you can detect it through the dispersion measure. And so isn't it amazing that the estimated cosmic dispersion measure agrees with the prediction of Planck cosmology? The gray zone here is accounting for, what you expect fluctuations in that just due to large scale structure in the universe, due to the cosmic web. You expect fluctuations in that. And so they all seem to lie pretty much within that gray zone. And so, Macquart and I argue that they have detected the missing cosmic baryons using fast radio bursts. Now, I think, there's a lot of room here. You can then try and invert it and estimate what the baryon density is from from these fast radio bursts and compare it to what you predict. You have to make a lot of assumptions about the host galaxies, but eventually, these are just 5 sources they've done this with. As I'm going to describe, we're going to have 1,000 sources soon. And so this will become easier and very interesting. We'll not only be able to measure this, we will be able to determine where in the intergalactic medium these cosmic baryons are, because they should also be, how are they distributed uniformly in halos, with what density configurations in the halos. So it highlights the importance and potential of fast radio bursts as novel probes of large-scale structure in the universe. And here's just a quick slide. Actually, there's a whole bunch of different cosmological or at least large-scale structure applications, potential applications of fast radio bursts, if you could find a lot of them. So I've listed them, and this is just a very small fraction of the papers on these topics. I don't want to get into all of them, but just to motivate that fast radio bursts have huge potential. You have imprinted on them the DM the scattering, scintillation. And I haven't started talking even about the polarization of the radio waves, where you can infer rotation measures, that is line of sight magnetic fields through the intergalactic medium. You have huge potential to use fast radio versus cosmic probes. And so you need to find more FRBs. And how am I doing on time? I think I have about 15 minutes left or so. Is that right? About 15 minutes?
Yeah, that'd be great.
Okay. So we would like to find more FRBs to determine their nature. You know, do others repeat? Maybe they all repeat if you wait long enough. We want to realize their potential as cosmic probes. But the problem is they're transient, they're brief, they're unpredictable, they're all over the sky. And it's hard for traditional radio telescopes to detect them. What you need is a telescope with a very wide field of view and very high sensitivity to be able to do this. And that's where this telescope comes in. It's called CHIME, the Canadian Hydrogen Intensity Mapping Experiment, which should immediately tell you the telescope was designed for an entirely different project. It was designed for a cosmological project to study redshifted hydrogen, redshifted neutral hydrogen, in order to study baryon acoustic oscillations and measure the equation of state of dark energy. But the design is wonderful for transients like fast radio bursts. So first of all, this is located in Penticton, British Columbia at the Dominion Radio Astrophysical Observatory. It consists of 4 cylinders. There's no moving parts. This is not your conventional radio telescope. Nothing moves here. There are 4 cylinders that are 20 meters by 100 meters long, and oriented exactly north-south. North-south, so that the sky is a transit telescope, meaning the sky rotates east to west every day, and we observe whatever is overhead. This is, it's Canadian, so I have to give the area in units. It's about 5, in Canadian units, about 5 hockey arenas. On the axis of each of these cylinders hang 256 dual polarization radio antennas. Dual polarization means there's 2,048 inputs. It says 1,024 antennas total, because there's 4 cylinders and each one is dual polarization. So it's 2,048 input signals. And these are sensitive in the range 400 to 800 megahertz, a little lower frequency than where the fast radio bursts that I've shown you so far have been detected. Now, this telescope, it doesn't focus in the north-south direction. It's a mirror in the north-south direction. So that means you see a huge swath on the skies. I'm going to show you. You have a total field of view of over 200 square degrees. And you compare that with, square arc minutes for a conventional parabolic radio telescope. This is phenomenal orders of magnitude higher. And this was built using funds from the Canada Foundation for Innovation for a total of 18 million Canadian dollars. This is the CHIME Fast Radio Burst team. There's probably cosmologists here, and you might recognize a lot of our steering committee are cosmologists. But we have a fantastic set of students and postdocs who do phenomenal work on this, and you can see our team here standing in front of CHIME and also standing along the axis. I won't dwell too much on technical details about how it works, but in short, those 2048 signals, they're digitized so that our input rate is total 13 terabits a second, which is comparable to the world's cellular network. This is a lot of data that we're getting here. We then have an FX style correlator that's based on FPGAs, cards that were built by the McGill Cosmology Lab led by my colleague, Matt Dobbs. And then an X portion of the correlator that's GPU based, built by my colleague at University of Toronto, Keith Vanderlyn. And all these signals actually can go simultaneously to 3 different instruments. One that does the cosmology, another that studies pulsars, and then one that studies fast radio bursts, and that's the one I'm talking about today. The way this works is if you have a cylinder and you just have one antenna, you see one huge swath on the sky. But if you populate it with many antennas and you essentially do an FFT of these, it's, you could think of it like a diffraction grating, you effectively see many independent beams on the sky. So we're tiling the field of view with beams. And if you then put antennas along all these different axes, what you see is that full 220 square degree field of view is tiled with 1,024 beams. So it's like we have 1,024 Green Bank telescopes or 1,024 Parkes telescopes, all operating at the same time. The data rate is enormous. And this is actually a beautiful, much more beautiful image showing really what 1,024 beams looks like. And this is made by our postdoc, Cherry Ng at the University of Toronto, and analytic work by Kyo Masui, who's our postdoc, but now faculty at MIT. We have a real-time detection pipeline where we buffer data and then delete it if we don't detect anything. You must have a trigger-based system, like in particle physics, for this to work. It's just too much data to collect. We have, here is where we do the beam forming, and we actually save all the raw voltage data as well. The individual beams and with polarization summed, sampled at 1 millisecond using 16,000 frequency channels that's a data rate of 142 gigabits per second. That's all searched for using supercomputers that are located adjacent to the telescope. So all this computing is on site. That's where the nodes are. There's 128 CPUs are used for the de-dispersion. You have to search over dispersion measure and then search for few millisecond pulses, in data 24/7. And then we have different, we have to make sure we throw away terrestrial interference, and we make sure the source isn't some galactic radio pulsar. Those are, they used to be my favorite thing to observe, and now they are contaminants. In any case, we save all this data, and in 2018, we discovered our first set of 13 FRBs, and yes, they do exist down to 400 megahertz. That was very exciting at the time, and you can see this montage of de-dispersed bursts. This was the number of fast radio bursts that were known prior to 2019. You can see a lot of them from the from ASCAP, some from the Parkes telescope. When CHIME, now CHIME is turned on, and the story is a little different. With the massive field of view, we've detected now over 1,000 of these events. So it just revolutionizes the field. This is as of 2019. We've continued to operate during the pandemic, without any problems. And so we have another one of these red bars we could show. I don't have that much time left, so I'm going to skip this just to mention we have our first catalog of FRBs has about 500 events. It's been submitted to APJ supplements. It'll appear online probably next week. It has been tremendously challenging to calibrate these data. You want to be able to say where they are on the sky. You want to say how bright they are. You want to say what our detection system is sensitive to. We have biases. It's harder to find higher dispersion measure events, for example. There's so much that you have to calibrate with this telescope. And we're just one team of students and postdocs working really hard to get all of this done. We found lots and lots of repeaters. We found 8 repeaters at first, and you can see all sorts of morphologies. They're color-coded by sources. All the green ones are from one source. 8 different repeaters, interesting pulse morphologies. We then found another 9 repeaters. Like it's like shooting fish in a barrel with CHIME. We go, the same part of the sky comes back every single day. So we are just constantly finding repetitions. And so basically there's a population of repeaters out there that we've discovered. One interesting thing that we've noticed is that the widths of the repeater bursts the repeater events, bursts from repeaters tend to be broader than bursts from apparent non-repeaters. And I say apparent non-repeaters because some of them might eventually repeat, we don't know. But here you can see the histogram of pulse widths for repeating. And here the blue are the non-repeaters. And you just see that the repeaters are broader. And, that suggests potentially different emission mechanisms or different classes of sources. It's quite interesting. This is work by Emmanuel Fonseca and Ziggy Plonis. I'm running out of time, so I'll just mention very quickly, without explaining this complicated slide, that one of our repeaters has shown a 16-day periodicity. We see it only every 16 days for a 4-day activity window, in spite of the fact that we have exposure all the time to this source. This is a periodogram just showing you that we see it's only roughly every 16 days. What happens every 16 days in this source? Magnetars don't do that sort of thing. Smells like an orbit of some sort, I think, but we really don't know why it's doing that. I'll mention very quickly, I'm skipping slides now because I'm running out of time. We recently detected a galactic source. This was an incredibly bright burst from a galactic magnetar detected by CHIME and also detected by a Caltech instrument called STARE-2. And this was by far the brightest magnetar burst ever seen in the radio. This is a galactic source now. So here's a nice summary plot. Here's a distance on the x-axis and the observed radio fluence on the y-axis as total observed energy. And here you see are the local radio pulsars, like the Crab pulsar. This was one bright galactic magnetar that showed quite a bright burst. And these here are the FRBs with their inferred distances. Gigaparsecs kind of distances, and they're inferred and they're measured fluences. And these diagonal lines are the total energies in the bursts. So what you can see is that, the FRBs in terms of energy are orders of magnitude higher than anything we've ever seen in the galaxy until this event. So this galactic magnetar detected with CHIME and with STARE was way brighter in the radio than anything ever seen from the galaxy. And in terms of energy, you can see that it's now comparable in energy to the lowest energy FRBs that we know. It's actually still, the gap is still about an order of magnitude, but we've closed a massive energy gap. If you think FRBs are magnetars, then this is great evidence for that. It doesn't prove it. And certainly there's still many orders of magnitude to go to get to the most luminous, most distant fast radio bursts. Are these also magnetars? We don't know. One other result that we have recently is we've detected a very nearby FRB. So this FRB is a very low dispersion measure, and yet it's much higher than what the galaxy can produce. And it's in the direction of a nearby spiral galaxy, the M81 galaxy, which is at 3.6 megaparsecs away. Very close. The chance probability of this, here's the error circle, being so close to this galaxy is less than 1%. And it may seem like it's well outside the galaxy, but galaxies have huge neutral hydrogen disks around them. The sort of neutral hydrogen gas that's detectable in 21 centimeter light. And this is where now the FRB sits in the neutral hydrogen extent of this M81 galaxy. So this is wonderful. It's a very nearby source. If you think they're magnetars now, go with X-ray telescopes and look. And it's a repeater, so you just have to be patient. And maybe we'll see X-ray bursts from it. It's very exciting. Except just last week, like there's so many twists and turns in this FRB story. Just last week, the European Very Long Baseline, the VLBI network, detected our repeater and localized it. It turns out there's a globular cluster in there, and it's bang in the globular cluster. So globular clusters are very well studied astronomical objects that are known to be really old, like really old stars, not magnetar kind of stars, not young stars at all. So that's like another shock. Like, what is that? We really don't know. So maybe this repeater is not a magnetar. Maybe this repeater is something else. Maybe this repeater is a crab-like giant pulses, or maybe it's something totally different. Some of them are periodic. Maybe it's some sort of binary system. We don't know. I've run out of time, so I will just very briefly flash up some catalog results for those of you who are interested. We have very quickly, for those of you who are familiar, our cumulative fluence distribution is consistent with a non-evolving population in Euclidean space. Whoops, sorry about that. The power law index minus 1.4. This is for aficionados really quickly. We have a measured sky rate. And we have evidence for a very large population of highly scattered, undetected events in our band that we can't see. But all of this, please see this paper that will be coming out next week on the archive. I'll skip that. I'll say very quickly, we have fantastic students doing analyses of this first catalog. We have one student looking at repeaters versus non-repeater morphology, and they're shockingly different, very interesting. We have someone who has looked very closely at the sky distribution to see, is there any correlation with the galactic plane? The answer is none. That's Alex Josephi who's done that work. Masoud Rafiei-Ravandi has done analysis of correlation with large-scale structure, and that's work in progress. Pragya Chawla has done a wonderful analysis of the DM and scattering distributions in our catalog, also work in progress. And Mohit Bhardwaj has another very nearby repeater localization that will come out soon. And finally, a look to the future. We'll soon be releasing public events using the VO event service so that in real time, you too can get your CHIME FRB events so you can do your follow-up. We're actively working on another repeater paper. We have a pile more repeaters we have to publish. And we're going to be building outrigger telescopes around North America, and from near one, not too far, one California. We're going to be building mini CHIME telescopes so that you don't have to wait for a repeater and go to VLBI, very long baseline or interferometer to get small localization, to get well localized FRBs. We're going to build these stations which will buffer data and wait for a CHIME trigger and then dump their buffer, and then we'll do VLBI on them. We hope to get 1,000 FRBs localized to 50 milliarc seconds. And that will enable a huge amount of redshift determinations, and will really be important for determining, for realizing their potential as cosmic probes. And that was my, we just broke ground in BC for the short baseline in Allenby, British Columbia. Very exciting. And that is all. I'll just conclude with another picture and thank all our collaborating institutions and our funders. I should have had somewhere, the Canada Foundation for Innovation disappeared, but they are responsible for the funding for this telescope. And I thank you all for your attention. I apologize for going a little long.
Well, thank you very much indeed, Ricky, for a lovely talk, which not only brought us up to date on what's been happening in this very rapidly developing field, but also conveyed, I think, to the whole audience the excitement of all the discovery that's going. And we know that next year you will give it a lot more progress and so on. So congratulations on your progress in this field, and also in repeat again on winning the Shaw Prize. can I perhaps just start with the first question, and that is, you sort of alluded to this, and if you think about supernovae and gamma ray bursts and so on, you always have this puzzle as to whether or not you're looking at 3 or 4 different physical systems at work when you have one sort of collective observational group with, say, in this case, fast radio bursts. Are you beginning to suspect that we're looking at 3 or 4 very different types of physical process at work, or do you think it's still tenable that they're all, for example, magnetars?
Well, so to me, the fact that the repeater bursts look really different, and now the short millisecond radio bursts, but I skipped one slide, but they're not only different in width, they're also different in spectral extent. So the repeater bursts are just tend to be band limited. And so to me, that says, oh, perhaps that could indicate different emission mechanisms. And there's also the variety of hosts, types and locations within the host. Like, to me, it smells like, oh, there's actually a variety of sources here, variety of types of sources. Now, does it have to be? If you look at, for example, solar flares, just solar flares alone, there's all sorts of different types of solar flares that look different, but they're all coming from the sun. And radio pulsars also, there's all sorts of different radio phenomenology there. You see giant pulses, you see, rats, you see periodic, you see all sorts of interesting phenomenology. So, and you can find young radio pulsars and old radio pulsars. So there could also be just an evolutionary relationship between among all these things. I think the jury's still out, but I would be really surprised if nature has only one way to make these kind of bursts.
Okay. Roger Romani, you have your hand up.
Hey,
Oh,
Roger.
hi. Yeah, hi, Vicky. Good to
Hey.
hear your talk. There's of course a lot of things I would like to chat about on this, but let me ask just one question. It's exciting to hear the progress about the outriggers. But something that I've always been a little puzzled by is it's a pretty sparse outrigger array, and you jump in an order of magnitude of baseline from 100 to over to 3,000. That's going to make a very funny beam. Are you going to rely on any sort of cross correlation with optical sources or something to select which of the peaks is the guy that you need, or how are you going to identify the positions, given that some of them are super faint galaxies or globular clusters in the outskirts? How are you going to do this?
So first of all, yes, it's a very sparse array, it's true, but all we want is a localization. So we're not imaging, we don't care about anything like that. We have the vast majority of these FRBs are very, the spectral extent is very broad. And so when you have broader spectral extent, you have a very interesting, it's easier. So we think that it's possible that way. And just to verify, really the group at University of Toronto, led by Keith Vanderlyn and also Wei Li Pen, have been doing this already using crab giant pulses at CHIME, correlating them with detections at the Algonquin radio telescope in Ontario. So there's an old radio telescope there, and there's also a 10-meter telescope, a smaller one, and they have been triggering it exactly the way we want to practice, and it's been working pretty well.
Okay, broadband helps. Thanks.
Yeah.
Tommy Chin, you have your hand up.
Yeah, thank you for the amazing talk. I'll ask one question, which is that, is there a range for the periodicity of the FRB?
Of the repeating FRB?
Yes.
Sorry, of the one where we found repetition, the 16-day guy?
Yeah, and then I was wondering if there's other periodicities, like how large is the range? Are they like other longer periods?
So there's only 2 where there have been reported periodicities. in the literature thus far. In the one I showed you really quickly, and I'm sorry, you could have had an hour-long talk just on that source, but it's 16 days with a 4-day, roughly 3 to 4 day window. The other one is the original FRB 1211, original repeater FRB 121102, which is, I think, 157 days. That one is not, it's because it's a much longer period. It's hard to see. You want to see many, many cycles to confirm a periodicity. So that one is not quite as statistically significant, but I think it looks very good. Those are the only two so far.
Thank you.
Vahe Petrosian, you have your hand up.
Yes, thank you, Vicky, for this nice talk. There's another aspect to FRBs because they have a hard redshift. It's about their cosmological distribution, which I'm sure if you had time, you could say a lot about it. But let me ask a couple of questions. I'm interested in this topic. First of all, about the dispersion measure redshift distribution. Now that they seem to come from dwarf galaxies, maybe the correction is smaller than we thought. And the second question I have is, in addition to fluence limit, which determines that provides the threshold for detecting, does the dispersion measure also come in play? If the dispersion measure is large, does that spread it too much to make it difficult to detect high dispersion sources?
Yeah, no, thank you for those questions. So first of all, I did emphasize the dwarf galaxy host of the very first repeater 121102. But what I was trying to convey afterward is that every other localization subsequently has not been a dwarf galaxy. You can estimate how much of a dispersion measure contribution should come from a face-on spiral galaxy, and it's not much. And we know that from the Milky Way because we have our own model. So for Milky Way type galaxies viewed face on, the contributions, 25, it's nothing, or it's very small. And curiously, you remarked on that one that was in the dwarf galaxy. In that case, we know the redshift, and the host contribution is actually relatively large. So in that case, the non-Milky Way dispersion measure is roughly equally divided between the intergalactic medium and the host, even though it's in a dwarf, and that's probably because it's in a knot of star formation. So the story is kind of complicated. If you see an edge-on spiral, well, you're going to have a really high dispersion measure, but then it depends, is it on the near side, on the far side? And now your second question, yeah, so the telescope selection function, I didn't have time to talk about this, but we are determining it very precisely, or trying to, we've set up an injection system. So we inject fake FRBs in real time into our system with known parameters, and then we see how well we detect them. So that way we can characterize how well our detection efficiency is as a function of different FRB properties. And you asked about dispersion measure. In that case, yeah, absolutely. It is harder to detect higher dispersion measure sources. And in that case, it's because there's residual, there's residual dispersion smearing in our channels, but it's not a huge effect. It's not a huge effect. It's a maybe, tens of % effect, and then increasing in higher dispersion, but the much bigger effect is scattering. And the CHIME band, we are losing huge amounts of highly scattered FRBs. We know this from our injection analysis. And so what I'm trying to say is that if dispersion measure were correlated with scattering, then that would be another reason we'd be losing very high dispersion measure events. Our current highest dispersion measure is over 3,000, if that's what you're wondering.
Okay, thank you.
Yellen, you have your hand up.
Yes. What can you say about the polarization of FRBs?
Yeah, I took all the slides out just because I knew I'd be over time. So it's kind of a potpourri. It's some of them we detect 100% linear polarization. Some of them we detect some circular polarization. Some seem unpolarized. So there's not and some of them where you have high linear polarization, you see constant, you can measure the position angle as a function of time during the pulse. In some cases, the position angle is constant over the pulse. In some cases, it changes over the pulse. So, like I say, I think the polarization story is fascinating, but really it's not clear what is going on. And moreover, once you have linear polarization, you can measure Faraday rotation. So this is the index of refraction in an ionized magnetic medium is different for one hand of circular polarization than for the other. And so the position angle rotates as a function of frequency, radio frequency. And this is now measured in all of the FRBs for which there's linear polarization. And some of them, the rotation measures are consistent with just being from the Milky Way galaxy. And in one case, the rotation measure is the largest rotation measure ever seen for any astrophysical object. Like 10⁵ radians per meter squared. And that happens to be the original repeater that's in the dwarf galaxy. So I'm getting really excited here. I have to calm myself down, but like what, so you asked a really great question and I don't have a coherent answer for you. There's so much going on. The answer's not clear. We just need a larger statistical sample. I hope eventually we'll figure this out.
Thanks.
Okay. Well, it's getting late, especially for you who are 3 hours in advance for us. Thank you once again, Vicky, for a lovely talk and a splendid way to end our colloquium series with a bang, or many of them. And keep well, everyone, and look forward to seeing people next quarter. I hope in person at the physics colloquia. Thank you very much indeed. Let's give a virtual round of applause to Vicky.
Thank you so much.
Thank you so much. Bye-bye.
It's been a pleasure. Just adjusting what's in the chat from Dan. I see Dan says that, oh, Hera can do it.
Oh,
Yeah,
but we
well,
have to
there's a chance
reprogram
Hera
the
can do it then. Okay, I didn't know Hera could do it. That's
Can
great.
you send us your
Yes, you might
students to reprogram it?
Send you what?
We need your students to reprogram it to look for dispersed pulses.
Hey, we have a wonderful bunch of students that will be coming on the job market soon. So yeah. And I see Jill, what's Jill say?
Jill has a comment too.
Yeah, I'm trying to see one suggestion for techno signature reviews that pulse changes. Oh.
I think Jill has left the.
She's left, but I understand what her question is. Yeah, we've never seen that. Like an abrupt change in period. Oh, we've seen glitches. Maybe she wants to call glitches that, but it's not really a change in, well, it is a change in period, but it's not an abrupt change from one period and back. Like, no, we've never seen that.
Yeah.
You'd get more than the Shaw Prize if you saw that.
All righty.
Okay, take care. Keep
Okay,
well.
thanks. Thanks, Roger. Yeah, I hope this was physicsy enough.
It was lovely.
Okay, wonderful.
Had a
Okay.
good and attentive audience.
All right, wonderful. Have a great rest of your evening or afternoon. Okay, bye.
Take care. Bye-bye.